Hi friends, let's continue our discussion. We are into third module, feature generation and feature selection. Now, after looking at details about the feature extraction, let's get into the next topic, that's feature generation. It involves creating new features from the existing ones in the data set. It focuses on selecting and transforming existing features. Now the question is why feature generation is required. The most important thing is to capture complex relationships between the features, between the data. These new features which were generated can increase the model performance. So if the data is not having proper features, then we need to generate new features and possibly that the model performance may increase. So we need to give a try, modify the features and verify will it improve the model performance. When it comes to non-linearity relationships in the data among the features, then it may be a bit easier to transform that some way and try to make it linear. So example would be if the data or the feature is showing something like exponential behavior with respect to any parameter, then instead of using the feature directly, if we can transform to the logarithmic of the feature, then the exponential can become linear. So once the feature becomes linear, then simpler models can be used to solve the problem. So we don't need complicated models when we do simplify the features. So it helps on addressing non-linearity in the data. Sometimes some data will be missing, and just because some feature, some values for any given feature, if they are missing, then it would be difficult to continue processing with this. Then one option would be add data to this particular missing, or we can altogether generate new features so that these missing data will not be a threat in model building and so on. The next issue is if we have domain specific insights about the data and the data is not appropriate to the domain we are working on, then it would be better to transform the features from the current way to domain specific feature, so that will simplify solving the problem, and hence the model becomes simpler, and the simpler the model, the training will be faster, and space and time complexities automatically get reduced. And most important thing is these new features can reduce overfitting. So the overfitting is a problem where the machine learns perfectly to the training data but gives worst performance for the testing data. So for training it's excellent performance, but for training it is worst performance. That's what overfitting is. So if we find that for the given data our model is getting overfitted, better transform the features into new possible features so that this overfitting can be reduced. So that's for feature generation. So here the new features from existing ones or the raw data are generated. Yes, of course, it requires creativity and domain knowledge to create new features. So it helps to solve nonlinear relationship problems, missing data, and we can include feature generation into the feature engineering pipeline and dimensionality expansions. So yes, in the earlier stage we were worried about reducing the dimensionality, but now if the given feature set is not sufficient to solve the problem, then we can create new more features using these available features and add to the feature set. So thereby the dimensionality is increased, and if increased dimensionality can provide a better solution, then definitely why not go for a little higher complication. The main motto has to be to have the best performance from the model. So while training, if we can take little extra effort, doesn't make any major problem. But taking little extra efforts during the training process, if it can give best results each time in future, definitely why not take extra pain in the training phase, and for that can be used for enhancing or increasing the dimension by adding new features. So that's through feature generation. Then yes, one another advantage is through transfer learning. So if we think that a model is available for some problem, so the a model is available for solving some problem, and if by modifying a little to our data or modifying a little of the results of the model can solve our problem, then why not use it? So that's a concept of transfer learning. In this, what we do is if a model is already available, so we can reuse this model and modify a little, like at the input the model may not match with our input, so we need to add one input layer so that our input matches with the input required for the model, and the output may not be the way we want it, so we can add one more final layer at the output side and train only the output layer, so that the whatever output the model is giving, we can retrain it, or we can fine tune it so that it solves even our problem. So that's a transfer learning. So to understand transfer learning a bit better, so let's assume that there is a model available which recognizes the fruits. So if we show the fruit image of any fruit, it will recognize. So whether it is an apple or banana or anything like that. So input is image. That means column of numbers. So each number represents one pixel content. So R or G or B value of a pixel will be a number. So we have a vector of numbers as input to the machine, and at the output we have number of outputs. So a classification model. So the number of outputs will be equal to the number of classes we have in our data. Now this is working perfectly. So show any image of a particular size, it will identify whether it's an apple or banana or mango or anything like that. So that's input is an apple, output the apple position goes high. If input is mango, then output mango position goes high, all others remaining low. That's how the machine is trying to tell us. But in reality, apple, mango, and all are our concepts. But at the machine level, if you look at it, each one is just a number, an array of number or a vector of numbers. Now, instead of showing fruit images, now you start showing other images like images containing animals. Now, if you just try showing the images, and if you find accidentally that the size of the image used while training and size of the image used for the new data, if they are matching, or we can pre-process and make them match. So our input images having animals can be given to the machine. So at the end we are giving again set of numbers, and these numbers get into the machine and processed, and finally one of the output goes highs. Now if we just continue experimenting, showing different images containing different animals, and if by accident if you find any consistency that every time a lion is shown, the apple output is becoming high, and every time a tiger is shown, a mango output is going high. If it is happening consistently, it might have happened accidentally, but if these results are consistent, then what we can do is on the last layer you change the labels. Where apple was written, now you write lion, and where mango was written, now you write tiger, and so on. Now a new machine is ready which classifies animals now. But in reality, the original machine was designed by someone else to classify fruits, but the same machine we are using with the little modifications or fine tuning the output, and it is now able to distinguish between the animals. So that's a logic of transfer learning. In this, what happens is the big task of training can be reduced. Just we need to just fine tune the output of any available model, and if available model after fine tuning can solve our problem, then that's it. So that's a new concept, or reusability is the new mantra of today. So don't try everything from scratch. Just look around. Somebody might have solved some problem, and just look seriously, and with little modifications, if you can use that model for your purpose, that's it. So that's smartness is required. So that's all about feature generation. So keep watching. We have many more issues to come. So till then, take care. Bye.